Good morning everyone. In last lecture we completed the third application of circular motion, that is banking of road. Before that, first was speed of vehicle on plain curve road, second was speed of vehicle in well of death, third was banking of road, first was the most safe speed. Then in last lecture we learned the upper limit of speed and lower limit of speed on banked road. Now there is again one, I think it is last application of circular motion, it is conical pendulum. So we have to study the motion of conical pendulum, its time period and frequency and corresponding relation with other quantities. You know simple pendulum, I hope you know simple pendulum. So this is a simple pendulum which is defined as a point mass suspended by this massless, flexible, we can say light, inextensible string from the rigid support. This is just a simple pendulum. But definition of simple pendulum, it is the point mass called as bob, it is metal bob, which is suspended by a massless, flexible, inextensible string from the rigid support. See here, this is the rigid support, this is the string, and this is a metallic bob, or it is simple pendulum. So first it is simple pendulum. Now we have to convert this simple pendulum into conical pendulum. What we have to do? Just displace this pendulum to one side and give a push in horizontal direction. Now this becomes conical pendulum. So what are you observing? The string which is connecting the rigid support and the metal bob performs a cone shape in the space, and due to this cone shape, this pendulum is named as the conical pendulum. What we have done, once again, displace this bob to one side like this and just give a push in horizontal direction. So this will perform a cone shape in the space. This cone shape gives the name to this pendulum as conical pendulum. So this is conical pendulum. So what is conical pendulum? A metal bob, a point mass fixed to one end of light, we can say massless, weightless, flexible, inextensible string from the rigid support, and when that pendulum is displaced to one side and gives a push in horizontal direction, it performs cone shape in the space, and that is why it is called as conical pendulum. So this is now conical pendulum. So this is light inextensible string, this is metallic bob, it is displaced to point B and gives a push in horizontal direction so that it performs a horizontal circular motion. So this is called as conical pendulum. We have to obtain expression for the time period of the pendulum. Here we can consider that small m is mass of that bob which is displaced through small angle theta with its vertical position. Capital L with the length of that wire, this length of the string which is connected with this metal bob, it has length L, and if it is displaced through small angle and pushed in horizontal direction, it performs a horizontal circle. Suppose that radius of circle is small r. In the displaced position B of this bob of the pendulum, that is, it experiences two forces. Number one, first is usually its weight mg. We have seen many times before. Weight of this metal bomb or simple pendulum acting vertically in downward direction. And second, tension in the string which is towards the point of suspension, towards the support. First force is weight mg which is acting vertically in downward direction. Second is tension in the string which is towards the point of suspension, means towards point A. This tension is a vector quantity. It can be resolved into two components. We know the resolution of vector. As it is vector quantity, it can be resolved into two components. First component is t cos theta which is vertically in upward direction, which is against or opposite to mg, means this t cos theta balances weight mg. And second is t sine of theta, component of this tension along the radius and towards the center of that horizontal circle. And we know the force acting on the particle performing circular motion along the radius and towards the center is called as centripetal force, means this t sine theta provides centripetal force and this t cos theta balances weight of the metal sphere or that bomb. So once again, हे जे मेटल स्फियर आहे तो एका बाजूला घेतला आपण, त्याला हॉरिझॉन्टल डायरेक्शन मध्ये ढकललं, तो अशी हॉरिझॉन्टल सर्कल परफॉर्म करणार, त्याची रेडियस असेल r, त्या लेंथ जी स्ट्रिंगची आहे ती आहे l, किती अँगल मधून बाजूला सरकवलं, थीटा इतक्या अँगल मधून, आणि ते जे बॉब खाली लटकवलेला आहे स्फियर त्याचं मास आहे m. जेव्हा तो हॉरिझॉन्टल सर्क्युलर मोशन परफॉर्म करेल, ह्या बी पोझिशनला त्याच्यावर काम करणारे दोन फोर्स आहेत. एक आहे त्याचं वजन डाऊन डायरेक्शनला, दुसरा आहे टेन्शन इन द स्ट्रिंग टुवर्ड्स दिस सपोर्ट. टेन्शन हे वेक्टर क्वांटिटी आहे, दोन कंपोनेंट मध्ये त्याला रिसॉल्व केलं. वर्टिकल कंपोनेंट असेल टी कॉस थीटा जो की बॅलन्स करतो mg ला, आणि हॉरिझॉन्टल कंपोनेंट आहे टी साइन थीटा जो की सेंटर कडे आहे, त्याला मॅथमॅटिकली मांडवतात. This t sin theta provides necessary centripetal force, so we can write here t sin of theta is equal to m r omega square in terms of angular velocity. You can also write the same in terms of linear velocity, mv square. So t sin of theta equal to m r square, centripetal force towards the center of circle. Call this as equation number 1. And second is t cos of theta which balance the weight of that metal bomb, so it is t cos theta equal to mg. Divide equation 1 by 2, we can write here t sin of theta divided by t cos of theta equal to here m r omega square divided by mg. On right side there are similar term mass get cancelled. We can write this expression for omega square. Again this t get cancelled. So using this relation we can write for omega square. This omega square can be written as g to this side means g into sin of theta divided by r to this side here r into cos of theta. So finally we can write omega as, this omega can be written as square root of g sin of theta divided by here r into cos of theta. Now see the figure carefully again. So this is original length or you can height, this is suppose L and this is r and this is angle theta. So in figure we can write sin of theta is equal to, we know, opposite side upon hypotenuse. So this is small r by capital L. So small r can be written as L into sin of theta. So put this value instead of r here. So we can write this omega as square root of g, it is sin of theta divided by, instead of small r, L into sin of theta into cos of theta. The sin theta get cancelled. So finally we can write this omega as The sin theta get cancel. Here remains only G divided by this L into cos of theta. So this is expression for angular velocity of this pendulum or conical pendulum. We can say angular velocity of conical pendulum. This is omega equal to G by L into cos of theta. It is clear that G and L are constant. So omega depends upon cos of theta. So omega is inversely proportional to cos of theta. But we know that this omega equal to 2 pi by capital T or 2 pi n, where n is frequency. So we can write here, therefore 2 pi by capital T is equal to square root of G by L into cos of theta. So finally we can write here capital T equal to 2 pi into square root of L cos theta divided by G. So this is formula for time period. T is equal to is 2 pi into L cos theta divided by G. So this is expression for the time period of conical pendulum. We know the definition of time period. Time taken by particle to complete one revolution. So this conical pendulum complete one revolution in this much time. It is clear that again this capital L and G are constant. So capital T also depends upon cos of theta. Finally, n equal to 1 by capital T. Therefore, this frequency is equal to 1 by 2 pi into square root of G by here L into cos of theta. So this is expression for frequency of revolution of this conical pendulum. So frequency of revolution of conical pendulum is n equal to 1 by 2 pi square root of G by L into cos of theta. It is again clear that this frequency of conical pendulum and time period of conical pendulum depends upon angle theta, cos of theta, as G and L are constant. So this is expression for time period and frequency of revolution of that conical pendulum. So in terms of tan theta also you can write this expression omega. Here you can write sin theta upon cos theta as tan theta. So it is equal to, in short you can write this as G into tan of theta divided by R in terms of tan theta also if you consider theta. So this is the expression for angular velocity. This is the expression for time period and frequency of revolution of conical pendulum. So it is clear again, if we consider theta equal to 0, it is not displaced through small distance and given a push in downward direction. It just looks like a simple pendulum. We will study the simple pendulum in oscillation, chapter oscillation. And again one condition, if we consider here theta equal to 90, what happens? The string becomes horizontal. If theta equal to 90, cos of 90 is 0, so L becomes infinity. So if we make angle equal to 90, means it cannot be considered to be a conical pendulum. It performs just horizontal circle parallel to the rigid support. So for such pendulum, conical pendulum, the frequency will become infinity. So if we go on increasing the angle at one stage, the string becomes horizontal, so it performs horizontal circular motion, and in such case this mg is acting vertical and downward direction, but there will be no any component of tension. The tension will be just towards the support or towards the midpoint at center of the circle, so you cannot resolve the tension. So these things also we must remember here. So this is conical pendulum starting from its definition, then figure in very small that is simple language we can write the explanation here. We have to read this figure and then we have to obtain expression for time period considering these two expressions, that is t sin theta equal to m r omega square, t cos theta equal to mg, dividing and considering another terms. So we can write for time period and frequency. This is the fourth application of circular motion. And conditions again, if you go on increasing the angle, what happens? It becomes horizontal. At that time its frequency becomes infinity. So, and tension acting towards the support. So this is in conical pendulum, an expression for conical pendulum. Next, in next lecture we will study the vertical circular motion.